So let's talk now about wayfinding. Wayfinding basically is finding your way, of course, being able to navigate from one point to another point. And one of the things we do when we're finding our way to different places or in different locations is we use landmarks, right? And landmarks are objects that on our route that we use as cues to indicate what direction to go. And of course, we do this. We do this when we're driving or walking in a strange city. If you want to find out, for example, one of the things that I do when I travel to a different city each time is whenever I have to walk to work or walk to a subway station, I always make note of the buildings that I see and signs that I read on the way. That way, when I'm trying to find my way back to my hotel, I'll use those things that I remembered as landmarks. Obviously, a very useful skill to have, something that we all need to do. So there was a study done by Hamid and Stankiewicz and Hayo in 2010. It's a fairly recent study. And what they did was they had people navigate through a maze, and they had a bunch of little landmarks there, little things that they could use to mark their way and remember the way out of the maze and through the maze. And what they did was they detected, or they used gaze detection equipment to tell which landmarks, which objects that the folks were using that the folks were looking at the most, that they were fixating their vision on the most. So they studied that, and they wanted to look at the relationship to see if there was a relationship between how much time the person spent fixating on a particular landmark and whether or not that landmark was actually used in navigating. And sure enough, if they removed the landmarks that were not fixated, it turns out it didn't make a difference, right? If they removed half of the landmarks that were not fixed, it turns out it didn't make any difference. So they didn't pay any attention. However, if you look at the two bars on the right hand side, when they removed half of the landmarks that had been fixated on, that the subjects were most fixated on, the performance on the maze significantly changed. The performance went down, telling us that yes, as we're navigating through an environment, and when we fixate on something, where the fixation serves as a way for us to use that landmark as a reference point to navigate through an unfamiliar territory. What parts of the brain are involved? Well, we've known actually for a few decades now, we've known that the hippocampus, which is this kind of purplish thing here, and this is a side view of a brain, but kind of a hollow view. So this is the front of the brain here. This is the top of your head. This is the back of your head. And so this is like the side of your brain, and just pretend that pretend that this part of the surface of your brain became see-through, so you could see through it. And the hippocampus is kind of is this area here. And if this was a three-dimensional drawing, the hippocampus would be kind of coming out at you a little bit. As it comes out like this, it would be sticking out of the screen a little bit. Because it curves like this, kind of curves like that. Okay, so that's your hippocampus and the retrosplenial cortex and the parahippocampal gyrus. These areas of the brain are really important in helping us to navigate and to map out space. We know this is something we've known for quite some time. Another experiment by Jansen and Turnerout, was used a virtual museum. I don't know if there's a picture of that here. Yeah, here's a picture of a virtual museum here, right? So they had, basically what they did was they had people navigate using a keyboard or a joystick through this virtual museum. And this virtual museum had like these little exhibits, like toys and things sitting on tables that you could use as landmarks. And it turns out that what they did is they were told that they should be able to act as a guide through the museum. So they said, okay, you have to know your way through this museum. So you have to know all the stuff, and you have to know how to navigate your way through the museum. They put exhibits, in other words, they put these toys, exhibits, at two different points, either at a decision point where in the pathway where you had to decide whether to go here or here, or they put the toys at a non-decision point, meaning the toy's there, but it's not related. It's not put in a place where you're going to be making a decision as to which direction to go. Okay. So essentially what they did was they then looked at the activation of and they were given they were put through this task, right? And to recognize, they had to know all the exhibits, because remember, they had to act as a guide, so they had to recognize the exhibits, what the exhibits were, as well as where they were, right? After they went through this learning task of going to this museum, they were put into an fMRI machine to look at the parts of the brain that were activated the most. And they were then presented with objects that they had seen as exhibits and new objects that they hadn't seen. Okay, so they showed objects that they saw in the exhibits and objects that they hadn't seen. And it turns out that the greatest activation in the parahippocampal gyrus, which is this part of the brain here, which lies next to the hippocampus and is very much involved in helping us to navigate through the external world. It turns out that the parahippocampal gyrus lit up quite a bit whenever you were shown an object that came from a decision point, which is really interesting. So if you basically, and it was both for objects that were remembered as well as those that were forgotten. So if you couldn't remember seeing the object, if it was related to a decision point, the activation was much higher than for objects that were not at decision points, which is telling us, right, that these objects act as cues. Even when they're not in their decision point environment, they act as cues, enabling us to understand and use them when we see them as navigation aids. Another way that we can study the effects of the brain regions that are involved in mediating wayfinding is to studying the effects of effects of brain damage. So there's this interesting case study that was reported in 2006 by a patient named TT. Now, TT was a cab driver in London, and he had been driving a cab for a long time, and he contracted a case of encephalitis, so infection of the brain, that destroyed, and the end result of this encephalitis was that it destroyed his retrosplenial cortex. He found out after he recovered from this encephalitis that he was unable to navigate very well in unfamiliar areas. So while he could navigate okay, remember he was a taxi driver in London, which is a really tough place to be a taxi driver because London is just laid out crazy. He was able to navigate okay when he was on main roads, the roads that he knew really well and that were very well indicated on maps and whatnot. But he had a lot of trouble when he went onto side streets. He wasn't able to find his way when he was on a side street, roads that he had known before, he had been on before, but he didn't use them very often. And what this tells us is that the hippocampus and parahippocampal gyrus are somehow involved in storing the information that we gather while we're finding our way, but that the retrosplenial cortex is probably really important for helping us to retrieve that stored information that the hippocampus and other parts of the brains put away for us. So what was happening with TT was that since his retrosplenial cortex was damaged, he was unable to pull up that old information from those old side streets he had been on before, and he was completely unable to know his way around because of the damage to his brain. Here's another example of a patient that had retrosplenial damage. So basically what happened here was, let me see if there's a picture. No, there's not a picture. Okay. Let me show you this real quick. This is a slide of the what the taxi driver, TT, this is one of the games that he had to play as he was driving. This was a simulated driving through London, and they asked him to navigate through London. And he was able to do it on, like I said, on the main streets, but not so much on the side roads. This picture is from page 162 of your book. It's another example of somebody who has retrosplenial cortical damage. Now, the task here is to identify where somebody took a picture of a garden table, okay, in this person's garden, right? So it's in your house, right? So somebody takes a picture of something in your house, and your job is to look at that picture and to tell me where the photographer was standing. Okay. Now, if you have an intact brain, this shouldn't be a problem. If I came into your house and took a picture of like a table or a chair or a wall, a picture on the wall, and I showed you the picture and I asked you, okay, where was I standing when I took this picture? You'd be able to look at that. You'd be able to go, oh yeah, I think you were standing right about here, and you wouldn't have a problem. This image here shows you the data that came from a woman with retrosplenial damage. Her guesses as to where the photographer was standing who took a picture of this table were the red arrows that you see here. But the correct viewpoint was here. She was completely unable to pull up information about her house and use it in determining in her mind relative spatial relationships. She wasn't able to do that, even though this was her house and she knew it, and she could tell you where things were. But whenever it came time for her to navigate or help somebody else navigate, it became a huge problem for her. Affordances. This is an extremely important concept, guys. Affordances. Gibson, J.J. Gibson, the ecological perception guy that we mentioned at the beginning of chapter 7, talked about this concept of affordances. And basically, affordances are what objects are used for. It's the information that we have about an object, about what it's for. And it turns out that we use that information in perceiving the object and in handling the object. So, for example, I have a flashlight here, right? And what is it for? Okay, what is it for? Well, I know what this flashlight is for. I know it's for shining light in front of me, for example, as I'm walking. So I know that in order to use this flashlight properly, I have to grip it like this and turn it on like this, and I know the proper way to hold it, approach it, and grip it. Okay, all of that information is what constitutes an affordance, right? It's the potential action that you can do with a particular object. You can think of anything like a cup, for example. Here's a cup, right? A Whataburger cup. And, I know what the affordance of this cup is. This affordance of this cup is for me to drink something. So I know that in order to drink something, I need to be able to grip the cup, hang on to it, grip the cup, hang on to it, and then bring it to my mouth and tip it so that I can get a drink. I know that that's all part of the affordance of the object. What's really interesting is that there are people with brain damage, some types of brain damage, in that the brain damage will basically cause them to not be able to name the object, but they can still describe how to use it and actually use it themselves. So if I have this particular brain damage, I would look at this object, and the doctor would ask me, Ray, what is this called? And I'm like, I don't know what that's called. But if the doctor said, okay, well, show me how to use it, I would be able to pick it up and use it as a flashlight. Very interesting that we have this distinction between naming objects and using objects. And Gibson encapsulated this using objects as affordances.